Bismillahirrahmanirrahim. This video is to provide an explanation on how to use the simplex method to solve linear programming problems. The credit is for these two sources. Linear programming means we are dealing with linear equations, and programming means planning, the best decision for a scenario or case we are dealing with, like the example in front of us. Nikki holds two part-time jobs, job one and job two. She never wants to work more than a total of 12 hours a week. She has determined that for every hour she works at job one, she needs 2 hours of preparation time, and for every hour she works at job two, she needs 1 hour of preparation time. And she cannot spend more than 16 hours of preparation time, and if she makes $40 an hour at job one and $30 an hour at job two, how many hours should she work per week at each job to maximize her income? The first step in any linear programming problem is formulating the problem, converting the real life problem from words into mathematical model. If we do so, we can see that the objective of Nikki is to earn as much as possible per week. She has $40. She can have $40 an hour from job one and $30 from job two per hour. If we assume that she works per week x1 of hours for job one and x2 for job two, then the total income per week would be z equals 40x1 plus 30x2, and the objective of the problem is to maximize z. So we need to decide how many of hours at job one, which are x1 hours, or how many x2 should be for z to be of maximum value. Because of this, x1 and x2 are called the decision variables. So to formulate any linear programming problem, we need to define the decision variables. The objective function, z is called the objective function. This is the objective of solving the problem. And then we must formulate the constraints. As stated here, Nikki cannot work, or she doesn't want to work more than 12 hours a week. So x1 is the number of hours per week for job one, x2 for job two. So this means that x1 plus x2 cannot exceed 12 hours, or cannot exceed 12. Mathematically, we can express this as x1 plus x2 less than or equal 12. We don't know how less than by how many hours, and they can equal 12. x1 plus x2 can equal 12, but they cannot exceed 12 hours. In a similar way, and as stated, 2 hours of preparation are needed per hour of work at job one, and 1 hour of preparation is needed for 1 hour for each hour of work at job two. Mathematically, this means that 2x1 plus x2 must be less than or equal to 16 hours. We are dealing with time. Time cannot be negative, so x1 and x2 must be non-negative. Mathematically, this means x1 must be bigger than or equals to 0. x2 must be bigger than or equals to 0. Now we have converted the real life problem into mathematical model. Before using the simplex method, we will solve the problem graphically for comparison, and as you will see, this is gonna help us. The graphical solution is possible when the problem has only two decision variables, which is the case here. We have two decision variables, x1 and x2. This means that we can use the graphical method using the Cartesian coordinates. We have four constraints in the problem. We have two decision variables, one objective function, and four constraints. The solution to be found, the optimal value of x1 and x2 must satisfy the four constraints. So to define the area of overlapping or the area that satisfy the four constraints, we will start by defining x1 bigger than 0, which means that x1 value must be in the upper half of the plane. X2 is bigger than 0. This means that x2 must be in the right side of the plane, which means that the first quarter is a primary feasible region for the solution, acceptable solutions. Then we'll graph x1 plus x2 less than or equals 12. We will make it to equation x1 plus x2 equals 12. We will plug in 0 for x2, giving us x1 equals 12. Assuming x1 equals 0, x2 equals 12. And now we have 2 points which we can use to draw the line x1 plus x2 equals 12. The point 12 and 0 and 0 and 12. The last constraint, 2x1 plus x2 equals 16. We can use the same way to have the 2 points 8 and 0 and 0 and 16. Having in mind the inequality signs, we can see that the feasible region would be the dotted area, in which any point in this area is a feasible solution, satisfying all the four constraints. To find the optimal solution, we will draw the z line by assuming a value for it, let's say 120, because we can divide 120 over 30 and over 40. As we did here, we can draw the line for z, moving it to the maximization direction till it touches the feasible region at the last point. The last point z will touch the feasible region would be the optimal solution, which is this point at x1 equals 4 and x2 equals 8. Plugging these two values for x1 and x2 in the equation of z, 40x1 plus 30x2, we can see that the optimal value for z would be 40. Now we need to start talking about simplex. After we converting the real situation or the real life situation problem, the wording problem, into mathematical model having inequalities, still we cannot use this model because of the inequalities. We don't know how many x1 plus x2 is less than 12, less than or equal 12. Similar, and the same applies for 2x1 plus 2x2. So the next step after formulating the problem for simplex method is to convert the mathematical model into standard form. We will replace the inequalities for the constraints into equal sign. We have here x1 plus x2 less than or equal 12. We will add a variable y1, which will be the difference between 12, the right hand side, and the sum of x1 plus x2. So let's say that the final solution would be x1 plus x2 equals 9. This means that y will be 3. 12 minus 9 is 3. In the same way, 2x1 plus x2 plus y2 equal 16. y2 represent the difference between the right hand side 16 and the sum of 2x1 plus 2x2. y1 and y2 are called slack variables. They represent the unused sources of the problem. Meaning that, let's say that x1 and x2 plus y1 equal 12, not for hours, let's say they are a raw material like wood, 12 meters of wood. If x1 plus x2 are 9 at the final solution, this means that 9 plus 3 will equal 12, and y1 would be 3, representing the unused wood. So the slack variables represent the unused or the wasted sources of the problem. In addition to converting the inequalities in the mathematical model, except the non-negativity condition, it will be left as it is. because if the solution is less than 0 or negative, it will not be acceptable. And we will add to the non-negativity condition the new slack variables y1 and y2. After that, we will convert the z equation, the objective function equation, into a zero equation. We will move the right-hand side, 40x1 plus 30x2, to the left. And so the equation of z would be minus 40x1 plus minus 30x2 plus z equal 0. The reason for that is that the formulation now, or the system of equations now, can be converted to matrices, which is the mathematical tool used by Simplex. So we are ready to construct a matrix form for this system of equations. But before we do so, we need to discuss the basic and non-basic variables. We have 4 variables and only 2 equations. We have x1, x2, y1, and y2. These are 4 unknown variables, and we have only 2 equations to solve them, or to find their values. This is underdetermined system, meaning the system has either infinite number of solutions or has no solutions at all. If the number of equations equal the number of unknown variables, then we will have a unique solution. If the number of equations are bigger than the number of unknown variables, there is no solution. In our system here, we have more variables than available equations, meaning we have an underdetermined system of equations. One way to solve this system is to assume a number of variables with 0 value, and we call them the non-basic variables. And we leave a number of variables equal the number of equations we have without 0 value. These are the basic variables. So we have here 4 variables. 2 of them we will assume as basic variables, non-zero value, and 2 of them will be non-basic variables with 0 value. We can solve with simplex, or we can solve them algebraically if the problem is easy. We have here only 4 variables. We can make a table, define x1 and x2 in the beginning equal 0 as non-basic variables, assume find y1 and y2, solve. We will have 2 equations for 2 for 2 unknowns. We will find y1 and y2, and then substitute in z equation and find z value, and then change the basic variables. Assume x1 and 1y and 1y1 are basic, x2 and y2 non-basic, and repeat till we find all possible ways or combinations of this. And then from the table we can find the optimal value of z. But in real life, problems would not be as easy as this one. We may have hundreds of decision variables, and the simplex would be faster and a more reliable way. As I said, we will convert the mathematical model into standard form, and then standard form into matrix form. In the matrix form, the normal way is to have a matrix for coefficients multiplied by the matrix of variables equal the vector or the matrix of the right-hand side. In simplex, the only change is to have the vector for the variables on top of the matrix. So we have the coefficients matrix in the bottom. On top of it is the vector for the variables, and then right-hand side in the same or the normal way to the right. We fill in the coefficients from the equations. We have here x1 plus x2 plus y1 equals 12. The coefficient of x1 is 1. We will put it here. Coefficient of x2 is 1. It's here. y1 has a coefficient of 1 under y1. And then there is no y2, so the coefficient of y2 is 0. There is no z, the coefficient of z is 0. We will add z here for better understanding. The right-hand side is 12. The second equation, we have 2 for as a coefficient for x1. It's here under x1, and we will fill in the row in a similar way. And then we have the z equation. We have minus 40 for x1, minus 30 for x2, 0 for y1, 0 for y2, because the slack variables added only on to the constraints, not to the objective function. The coefficient of z in the objective function is 1, and the right hand side is 0. As we said, we'll choose two uh, variables to be basic with non-zero value, and two as non-basic with 0 value. This is the initial tableau or initial iteration, in which we assuming the original point or the origin as the starting point. We are assuming x1 and x2 as non-basic variables, y1 and y2 are basic variables. And we add here a column to define which basic variables we are using. As seen here, we have y1 and y2 as basic variables. And to read this matrix, y1, or the basic variable listed in the column of basic variables, will have a value which is in the right hand side. So here we have y1 equal 12, y2 equals 16, z equals 0, and x1 and x2 equal 0, because as we said, we're starting at the origin. To confirm that this is correct result, if we plug in x1 and x2 in any of the equation, it must be satisfied. If we put or plug in 0 for x1, it will be 0. 0 for x2, it will be 0 again. Plus z equals 0, z equals 0, which is correct. If we put here, plug in here x1 and x2 equals 0, y1 equals 12, which is correct. Finally, in the last constraint, y2 equals 16 if x1 and x2 equal 0, which is correct. So to read this initial tableau, or the matrix in the system of equations in the matrix form, we have a basic solution of y1 and y2. x1 and x2 are equal 0. Y1 equals 12, y2 equals 16, z equal 0. Now we need to check if this is an optimal solution or not. The check is for the to be done on the row of z. This is the optimality check. This is a maximization problem, which I forgot to mention. The linear programming problem, or to solve the linear programming problem using simplex method, we need to optimize the solution. Optimize means maximize profit or minimize cost. In case the problem is maximized, we must have inequality sign as less than or equal. If the problem is minimize z, let's assume x1 and x2 are cost, then it will be a minimized problem. In this case, the inequality sign must be bigger than or equal if to use the simplex method. So we have a maximization problem. We have two less than or equal inequality sign. We can use the simplex method. Returning to the initial tableau, the optimality check is performed on the row of z. We have two negative values. Presence of negative value in the row of z in a maximization problem means that the solution is not optimal. In minimization problems, if there is any positive value in the row of z, this would mean that the solution is not optimal. The reason for that, we have originally z equals 40x1 plus 30x2. We moved the right hand side to the left to generate the standard form and the matrix form. But if we return them back, it would be z equals 40x1 plus 30x2. We assumed originally that x1 and x2 equal 0. That's why we have value of z equals 0. But any increase in x1 or x2 would mean an increase in value of z. If we have x1 equals 1 and x2 equals 1, this z would be 70. So 70 is bigger than 0. So the presence of negative coefficient in the row of z mean that the right hand side still have variable which can be increased, and as well z. So the value of z equals 0 is not optimal. The proof for that is that there are two negative values here. So we need to find different basic variables. We have chosen y1 and y2 as basic variables, gives us a value for z equals 0, which is not optimal. We need to check which, we need to find a different basic variable set to see which one of x1 and x2 would be listed in the basic variable column, or to enter the basic variables set. Again, we'll go back to the original z equation. We have here z equals 40x1 plus 30x2. A unit increment in x1 increases the value of z with 40 units. An increment in the value of x2 with 1 unit would increase that with 30 units. So the x1 has much or have bigger influence on the value of z. So we need to choose x1. Mathematically, we'll go back to the row of z and see the bigger or the most negative value, which is minus 40, which comes from here. And we will define this as the pivot column, meaning this is the column for the variable which will enter the basic variables set. So we know now that we need to increase the value of z, we need to enter x1 in the basic variables set. But which one would leave, y1 or y2? To know that, we will perform a ratio test or a minimum test. We will divide the right hand side in the two rows we have by the coefficients of the pivot column. This is the pivot column. It has two coefficients and it has two right hand sides. So 12 by 1 equals 12, 16 by 2 equals 8. This means that we can increase the value of x1 from the first equation up to 12 if we put y1 equals to 0, plug into x2 equals 0, then x1 would equal 12. The maximum value x1 can reach from the first equation is 12. But from the second equation, we have 2x1 plus x2 plus y2 equal 16. So if we plug in 0 for y2 and x2, 2x1 equal 16, x1 equal 8. So despite the fact that x1 can reach up to 12 from the first equation, but there is another constraint from the second equation preventing us from increasing x1 more than 8. So the value which you can use, the maximum value which you can use is 8. So y2 must be the leaving variable. So we know now that x1 should enter the basic variable set, y2 should leave because it has the minimum value in the ratio test or the minimum test, and we need to generate the next iteration or the next tableau. To do so, we have to put x1 in the column for x1 as a basic variable column. We can see here that y1 has 1 as in the cell for the intersection between the column of y1 and row of y1. The other values in the column are zeros. Similarly, for y2, I can see that the intersection of y2 row and y2 column is 1. Other values are 0. The same must be done here for the column of x1. This cell is the intersection between the pivot column and the pivot row, and this must be 1 because we will list x1 here. So this must be 1, and this one must be 0, and this one must be 0. To do so, we will use the elementary row operations. for the matrices, which are very simple. The idea comes from the equations. If we have two equations like x1 plus 2x1, 2x2, I'm sorry, this 2x2 equal 3, and 3x1 plus x2 equal 5. To solve this problem, we need to eliminate one of the two variables. So we can multiply the first equation with minus 3. This gives us minus 3 here. Minus 6 equals minus 9. So by adding the two equations together, we'll have minus x2 equal 4 and x2 equal minus 2. The same, these are the two elementary row operations. The first one is we can multiply any row in the tableau with a constant, because this is similar to multiplying the two sides of the equation with a constant, like we did here, multiplying by 3. As well as long as we multiply it for both sides, the equation is satisfied. The second row operation is after we multiply, we add two rows together as we did here. We multiply minus 3 in the first equation, and then we add the two equations together. Doing this, we had here 2. So to convert this to 1, or to replace it with 1, we'll divide by 2 this cell. If we, as I said, if we do it for one cell, we must do it for the whole equation. So we will divide the whole row with 2, gives us 1 under x1, half, 0, half, 0, and 8. Now we have the pivot element with a value of 1. We must have the other two cells value as 0. We can do this by multiplying the row here with minus 1, and then add the two rows together, R2 and R1. If we do so, this will be minus 1 plus 1 equals 0. Applying the same for the whole row will give this row. The same should be done for the coefficient in Z row. We have here minus 40 and we have here 1. So if we multiply 1 by 40 and add it to the minus 40, it will give us 0 here. As we did for this cell, we'll do for the whole row here and here. So we will multiply each cell here with 40 and add it to the cell lower to it. We will have a new row for Z. Now x1 column is in the basic variable format. It has 1 for the intersection between row of x1 and column of x1, and zeros otherwise. And now we have the next iteration for the matrix 4. We have two new basic variables, y1 and x1, with the solution reads as y1 equals 4, x1 equals 8, and then equals 320. To check if this is correct, we must plug these values in the equation of z, which is 40x1 plus 30x2. x2 is not in the basic variable set, so it's 0, and x1 equals 8. 40 by 8, it is 320. This means that this table is correct. We need to check the optimality again. On the row of z, we have a negative value. This means that still this solution is not optimal. And again, the reason for that, we have here x1 equals 8, which means that z equal 320, and there is a negative 10 here, means that x2 has a negative of positive 10 here. So z equals 320 plus 10 x2. So still x2 can be increased, or any value of increment in x2 value would increase z. This means that, which means that the value of 320 is not optimal yet. We have to repeat the same technique again. We'll choose the most negative value in the row of Z, which is minus 10. This would be the pivot column representing the variable which will enter the basic variables set. And we need to perform the ratio test to see which variable will be leaving the basic variables set. We have here 4, and on the pivot column we have a coefficient of a half, or 1 by 2. So 4 by half, it's 8. 8 by half, it's 16. This means that y1 would be the leaving variable. We will add x2 in the basic variable set, and we have to convert the row of x2, the column of x2, to be in the basic variables format. The pivot element must be 1. It is 1. We can do this by multiplying the row 1 by the first row by 2. If we do so, we'll have this new row. To have this value and this value equals to 0, first we'll multiply the first row by minus half and add it to the second row. And later we'll multiply the first row by 10 and add it to the row of Z. This will give us the iteration 2 tableau, or the tableau number 2. We can see in this tableau that the basic variables now are x2 and x1. x2 equals 8, x1 equals 4, and z equals 400. And we can see that there are no negative values in the row of Z. This means that we have reached the optimum solution, and we should stop here. Because if we read the equation of Z from the row of Z, it reads as Z equals 400 minus 20 y1 minus 10 y2, because this is the standard form. If we return the values here to the right hand side, it would read Z equals 400 plus minus 10 y2 plus 20 minus 20 y1. Since y1 and y2 are not in the basic variable set, their values are 0. So Z equals 400 plus 0 plus 0 equals 400. There are no negative coefficients in the row of Z, meaning there is no variable in the Z, in the equations of Z, can be increased to add value to the Z, to the value of 400 for Z. So this is the optimal solution. We can stop here. And I forgot to say, here we start at the in the initial tableau at the origin. x1 and x2 equals 0. There is a fundamental theory in the linear programming states that the solution for the linear programming problem would lie on a corner point or an extreme point. We have here 4 corner points: 0 and 0, 8 and 0, 4 and 8, and 0 and 12. Any other point is called interior point. Either it lies on the line between 0 and 0, 0 and 0, and 0 and 8, or inside, or any other line, or inside the feasible region. So we have 4 corner points, and as per the convexity theory in the linear programming, the solution must lie on one of the corner points. The simplex does this automatically, because when we choose the basic variables, we defined two variables with 0 value and 2 non-zero values. By doing so, we moved from 0 and 0, the origin at the beginning, to the point 0 and 8. This was the solution here. And finally, we moved to the point 4 and 8. So the simplex method allows us to move the solution from the origin to one of the other corner points till we reach the optimal solution. Thank you very much for watching. I hope the video is useful. Thank you very much again.